We've looked at quadratic relations in y equals mx plus b form, which is slope-intercept form. We've also looked at them in standard form and converted from standard form to slope-intercept form. Now what we will be looking at is quadratic relations in factored form. So in this Minds On, I'm going to introduce you to some of the characteristics of the factored form equation. Here I have two factored form equations, and what you're going to be doing is filling in this table of values for each of these equations and then graphing them using Desmos. I would like to encourage you to try this on your own. If you're not sure what to do, then you can follow along with me. Otherwise, come back and check afterwards to see how you've done. So what we have here are two equations in factored form. Y equals 4 times x plus 3 times x plus 2, and then y equals 4 times x minus 1 and x minus 4. Each of these has three factors. 1, 2, 3, 1, 2, 3 factors. And you'll see here that I already have an example of the calculation, putting negative 4.5 into this equation, and then the example of putting 0 into this equation. So here we're replacing the x with its value, minus 4.5, and when you work that out in your calculator, you get 15. In this equation, we're putting 0 in for the x, and then calculating, and you get 16. So what we want to do is go ahead and continue filling these in. Now you don't have to keep writing this out every time, you can just do the work on your calculator. This next time I am going to write it out just so you can see again what's being done. So we're replacing now the value minus 3. Minus 3 plus 3, and then minus 3 plus 2. So I've replaced the 3 in where the x's are in this equation. And this one turns out to be an easy one to evaluate because minus 3 plus 3 is 0. And so I'm not going to put that in my calculator because I know that 0, which is in this bracket, times anything is 0. Looking at minus 2.5, putting that into my calculator, 4 bracket minus 2.5 plus 3, and then minus 2.5 plus 2, and that gives us minus 1. Next number is minus 2. And anywhere along the way, it's good to do your mental math. Once again, I see that minus 2 plus 2 is 0. 0 times any number is going to be 0. And the last value is negative 0.5. Negative 0.5 in this bracket and negative 0.5 in this bracket. This has some decimal values, so I'll put it into my calculator. And that works out to 15. Now I'm going to make that graph using Desmos. What we will need is these values here. We're going to click into the graph editor. And we're going to add a table. So you click table, and this allows you to put X and Y values in. So I will have to go back and forth a little bit. I'm going to scroll this down to help me, because then I can see these values here. So the first value is minus 4.5, and then we have 15. Minus 3 and 0, minus 2.5 and minus 1, and minus 2 and 0. And looking down, we also have minus 0.5. And 15. Now you'll notice that those points now are being graphed in Desmos here. And so we can scroll in and out. For now, we're just going to scroll out or zoom out just to see where we're at. So there are points, and there's the 15s. Now eventually, like we've done in the past, we're going to make this look better using the gear tool. It would be good to have this balanced. This is minus 3 right here, and this is minus 2.5. If we were at this 2, that would be a good view of this graph. From 2 to minus 2 is 4, so this is 4.5. So if we went 0.5 this way, that's still another 4. 1, 2, 3, 4. That would be minus 7. So we're going to go from minus 7 to 2. And then we know our points here are 15, so we can just go above those. We could go up to 20. So here I said we would go minus 7 to 2. And here we will go a little bit below the x-axis so we can see that. So let's go from minus 5 to 20, which is above the 15. And there's a good view of our graph now, and I'm going to insert that. Now we'll take that graph and move it over and make it larger so that we can refer to it later. So there's our first graph, and now we're going to do the same with the second one. We'll go ahead and fill these values in. We will have 1 minus 1 and 1 minus 4. Similar to the other question we did, we have a situation where 1 minus 1 is 0. 0 times anything is 0. $2.5 is next. Four times 2.5 minus 1 times 2.5 minus 4 gives us minus 9. Four minus 1, 4 minus 4, 4 minus 4 is 0, times anything is 0. And the the last value to do is 5. Five minus 1, 5 minus 4. 4 times 5 minus 1 is 4. 4 times 4 is 16. Times 5 minus 4 is 1. 16 times 1 is 16. So there are all of our values filled in. And we're ready to graph this equation now. We'll clear this equation, clicking the X, and we're going to clear this table and start from scratch. Starting with 0, the answer is 16. 1, 0, 2.5, minus 9, 4, and 0, and 5, and we had 16 there. So there's our points. And so what I'm going to do while we're at this, I will use these points here, and I'm going to center our graph now. Coming into the tool here for setting the values of the graph, it goes from 0 to 5. So let's go a little bit to either side. So let's go from minus 1 to 5, or 6. And then let's go from the lowest point, which is minus 9. So let's go from minus 10. The highest point is 16, so let's go to 18. And they wouldn't have to be those values, but something that shows us all of our points. Before I put that into the graph, I want to just check my points and also have the whole parabola represented there. So we're going to put the equation in again. Y equals 4 x minus 1 x minus 4. And there's my graph, and I will insert that. Here is my second graph. Now that we have both graphs in here, we can make some observations. So what I'd like you to do is take a moment and look at the graphs, look at your table, and see what observations you can make between this graph and that table. And then when we're done that, we'll take a look at what's called first and second differences. So looking at the table, one thing I notice is that the values repeat themselves as I go through here. Notice the 0 and the 15 and the 0 and the 15. And this minus 1 is the vertex. So on either side of the vertex, these values repeat themselves because parabolas are symmetrical. So we're just going to make some notes here to ourselves. The values repeat themselves. The values repeat on either side of the vertex. Something else to note is that in the equation, we have this 3 and this 2. Notice that the parabola crosses the x-axis at -3 and -2. Also notice that we had that situation with -3 and -2 where the bracket went to 0, and that resulted in the value of the y being 0. So what we're seeing here is that these numbers in factored form tell us what the zeros are going to be. The opposite number of x, when we put it in here for either of these, results in a bracket that's 0 and makes y 0. So the opposite number in each of these brackets are the zeros. If we take the numbers in the brackets if we take the numbers in the brackets and switch their signs, we get the zeros. If we take the numbers in the brackets and switch to the opposite sign, we get the zeros. Now what we're going to do is look at these differences here. So differences are when we find out what it takes to get from this y value to the next one. The other way of saying that is y2 minus y1. So I'll just write that up here. y2 minus y1, or the second one minus the first one. So the way we can do that is look at 15 and 0. To get from 15 to 0, that's down 15. So that would be negative 15. From 0 to negative 1 is down 1. From negative 1 to 0 is up 1. So that's a positive 1. And notice that if I did the y2 minus y1, 0, subtract negative 1, minus minus is a plus, so 0 plus 1 is 1. Up here, going from here to there, y2 minus y1, 0 minus 15 is minus 15. Minus 1 minus 0 is minus 1. Going from 0 to 15 is plus 15. And then when we get to the last one, there's an empty spot because we don't know what the next value is. So there's our first differences. So the second difference is we do the same thing with the differences. So here we're going from minus 15 to minus 1. That's up 14. Now what you'll find is we already have a text box here, so we'll just have to use this same text box to fill in the other table. So that's up 14. This next value goes from -1 to 1. That's up 2. From 1 to 15 is 14. Coming over to this table, from 16 to 0 is -16. From 0 to -9 is down 9, or -9. From -9 to 0 is up 9, so that's a +9. From 0 to 16 is up 16. Looking at the second differences now, from -16 to 9 is up 7. -9 to 9 is 18. -9 to 16 is 7. At this point, this is to illustrate what first differences and second differences are. You would have done first differences in the past with linear relations. With quadratics, we look at first differences and also second differences. At another time, we'll look at a table where these are equidistant in the x values to get a better understanding of what happens with the second differences. At this point, I'll just note with you that some of these values turned out to be exactly the same and the same sign, the 7 and the 7. We would be able to notice a very clear pattern if we had all of these x values equally spaced. Now we're going to use the observations that we've made in order to look at the graphs and the connection between this form, which is called factored form. So looking at this parabola here, we want to write the equation for it. Eventually, we would like to learn how to find this a value, but in these examples, I've simply given you the a value so we can focus on the zeros. So in this graph, I know that the a value for this is 0.5, so we're going to add that in here. A equals 0.5. So now we'll go ahead and write the equation. Going into equatio, and looking at that form that we have, y equals a is 0.5. X minus, and the first 0 is -2. So I will put another bracket since we have another minus. And the second bracket, we would have x minus, and the 0 is 3. And so what happens is that that minus inside of here ends up changing these signs, as we said. Y equals 0.5 x plus 2, x minus 3. So there's our equation for this parabola in factored form. And again, we could have went directly to this equation knowing that we could have gone directly to this equation knowing that we switched the signs of the zeros. Y equals 0.5, x, this is minus 2, so we make that plus 2. X, this 0 is positive 3, so we make this minus 3. So you're welcome to go directly to this equation from the zeros. If you prefer to use these minuses and then do the math that way, that's fine too. And so there we have our final equation for this graph. And that's what we're going to practice doing from here on in, is making equations for these graphs. So I'd like you to go ahead and make the equations for these graphs, and then come back and check. And then what we're going to do is go on to converting from factored form to standard form. So doing this next equation here, and these have the a values for us. Y equals a 0.5, x, the first 0 is minus 5. So I will change the sign and put a plus 5 in here. And x minus 4. There's a positive 4 for the 0. So that is minus 4, and there's the equation for that parabola. Looking at this next parabola, we have minus 0.5. We have 1, so this would be minus 1 in the first bracket. Our 0 is 5, so that would give us minus 5 in the second bracket. Here we have 2 for our a value. The first 0 is minus 4, so we will change the sign and make it plus 4 in the first bracket. The second 0 is 4, so we will simply put a 4 in there and leave the minus. And this final graph a is 3. Our first 0 is minus 5. We will change that to plus 5. Our second 0 is simply 0. Now when we do that, we end up with a 0 in here. But we don't leave zeros, we simplify those. So coming to the next line here, y equals 3x plus 5 bracket, and then we just have an x, so we don't need a bracket anymore. Now we could leave it like that, except the math convention is that if you have an x standing on its own, you would put it at the front after the 3. So we're going to do that to follow the math convention. So this would look better as 3x times x plus 5. And that is the equation for that graph. The next step is to look at going from factored form to standard form. In order to do that, we're going to practice some skills from grade 9, which is simplifying when we multiply factors together that involve variables. Two times x is simply 2x. 2 times 4x is 8x. X times x, that's 2 x's multiplied together. We use exponents for that. So that's x squared. And I'm using the up arrow to put that exponent, or the caret that's above my 6 on the keyboard. And 2x times 4x, two times 4 is 8, and x times x is an x squared, so I'm going to put x, use the up arrow above the 6, and put a squared on there. Now we're going to look at multiplying numbers together in terms of area. And that's going to connect to what we do with quadratic relations in terms of going from factored form to standard form. So what I'd like you to do right now is calculate the areas of these two So what I'd like you to do is calculate the areas of these two squares. This square has just one big section, whereas this square has multiple small sections. So in this case, I would like you to calculate the area of each of the smaller squares and then add them up to get the area of the large square. So in this first example, area is length times width. And our length and our width in this case are 10 and 10. So I'm replacing the L and the W with 10 and 10. So the area is 100. In this graph, I will need to do the area a few times. So looking at this first square, that area is 6 times 3. That equals 18. The next square is 6 by 7, so that's 6 times 7. And 6 times 7 is 42. The next block is 4 by 3. The last area is 4 by 7. And that's 28. Now that we have all the separate areas, what we'd like to do is add these up. So what we have is total area (18 plus 42 plus 12 plus 28), and you probably already have expected the answer to be 100. And this illustrates a point about the areas in these triangles and calculating them. This square is 10 by 10, but this one is actually 10 by 10. 6 plus 4 is 10, and 3 plus 7 is 10. And yet there were two ways that we could calculate that area. We could break it down into components. So here we did 6 times 3 and 6 times 7. Then here we did 4 times 3 and 4 times 7. So the answer to this question is that the areas are equal, and it's because they actually have the same length of sides. The areas are equal because they have the same length of sides. Now I'm going to have you go through an exercise that when we're using numbers may not seem so useful, because typically we learn to simplify the brackets, but eventually we're going to have variables in here and we won't be able to simplify because we won't have like terms. So what I'd like you to do is see if you can complete this operation without simplifying the brackets first. And the clue is looking at what happened inside of this square when we broke it into parts. What we can do is think about 6 times 3, 6 times 7, which is distribution, and then 4 times 3 and 4 times 7, which is similar to what happened up in this square. So the next line would look like this. And I'm going to show all the steps first, and normally then we would calculate the values, but let's show what we're doing here as operations. 6 times 3 plus 6 times the 7 plus 4 times the 3 plus 4 times the 7. And if you look back at the square above, you'll notice that each of these represents the areas of each of those rectangles within that square. So we end up with the same numbers we had at the bottom of that square. 18 plus 42 plus 12 plus 28. And that added up to 100. This process here is what we want to learn to apply, where we take the numbers in each bracket and multiply them through by the second bracket. And the purpose of doing this with numbers is to help you to see that it truly does work, and also with looking at the areas to connect it to something visual. Now what I'd like you to do is try the same process on your own using variables. In the first square, we have 2x times 2x. So the area is equal to length times width. Area equals 2x times 2x. That results in 4x times x, which is x squared. And in this next square, we're going to go through the process of breaking it down into these rectangles. And in this case, I'm not going to rewrite all of the areas. We're just going to do the areas. So the first example is 2x times 2x, and that equals 4x squared. The next square is 2x times 7. And that equals 14x. Then we have 4 times 2x. Four times 2 is 8, and there's an x, so that leaves us with 8x. And finally, 4 times 7, which is 28. 4 times 7 is 28. Similar to the example with numbers now, we want to take this and add these up as much as we can, where we would simplify any like terms. And I see here that the like terms are these two x terms, whereas these two terms are not like to any of the other ones. So we'll start with the first box and work our way through. I'm going to go from 4x squared to both of the x's and then to the 28. 4x squared plus 14x plus 8x plus 28. Simplifying the middle terms, 4x squared plus 14 plus 8 is 22x plus 28. So there is our expression for this particular square. So there is our expression for this square. Now what we're being asked to do is substitute x equals 5. So what that's saying is if x were 5 in these questions, what would be the actual area of the square? And notice that in this case, if x is 5, that makes this side 10 and this side 10, and that should sound familiar to what we had just done. Put the 5 into the dimensions of each of these squares and calculate what their area is using the formula area equals length times width once again. So what we have is 2x times 2x. And now we're going to substitute 5 in for the x. That equals bracket 2 times 5, and then 2 times 5 again, replacing the x with 5. That equals 10 times 10 for the dimensions, and that equals 100. So we'll substitute 5 into the dimensions. So we'll substitute 5 in the dimensions and use the area formula to calculate the area of the square. Two x times 2x, which looks familiar to our expression that we came up with, except that we're going to substitute right away. So we have 2 times 5 and 2 times 5. That equals 10 times 10, which equals 100. Now we'll do the same with this square on this side. its dimensions are 2x plus 4 times 2x plus 7. And so we want to put 5 in for the x. 2 bracket 5 plus 4, and then 2 bracket 5 plus 7. Now we will simplify the brackets using BEDMAS. So 10 plus 4 is 14, and then 10 plus 7 is 17. That equals 238. Now that we've calculated the areas using the dimensions, we're going to use these formulas that we came up with for the areas of these squares. The first formula is 4x squared. 4x squared equals 4 bracket, we're replacing the x with 5, and that's squared. That equals 4 times 25, which is 100, which is what we would expect. Now we'll do the same thing with this expression that we have here. 4x squared plus 22x plus 28. Four x squared plus 22x plus 28. Substituting 5 in for x, 4 times 5 squared plus 22 times 5 plus 28. That equals 4 times 25, which is 100, plus 5 times 22. 5 times 2 is 10. 5 times 20 is 100, so that's 110. Plus 28 gives us 238. As you can see, the two values in both cases work out to the same amount. That's what the purpose of these questions is to consider how they compare. Since they both work out to the same value in each case, I'm just going to write one answer for them. In both cases, the values from multiplying the length and width were the same as using the formula. And the reason we would give for this being the same is the fact that the formula represents the area including the x value that's missing from the dimensions. The formula represents the area of each square including the x variable that represents the missing value in the dimensions. And so now you can see that these formulas do work correctly. As well, you can see that this pattern of multiplying each factor also works. So we're going to be practicing using that strategy of distributing, is what it's called, the factors through the brackets in order to go from factored form to standard form. So here I'm going to illustrate that example, and I'll have you practice putting the factored form back onto the squares, and from there you can go ahead and practice the skill. So let's now go over this pattern of multiplying the terms through using distribution. We'll be using equatio again. When we do this, we multiply the 2x times both of these terms, and then the 4 times both of those terms. Two x times 2x is 4, and an x times an x is x squared. And I'm going to put an equals in front of here. 2x times 7, 2 times 7 is 14. And then we have an x. Now starting with the 4, 4 times 2x is 8x. And 4 times 7 is 28. Now we simplify the middle terms. 4x squared plus 22x plus 28. And you can see that compares to the question that we were just doing. So what I would like you to do here is go and try doing that expansion for each of these and converting from factored form to standard form, and then labeling these parts of the factors on the squares and using that strategy of finding the areas of the squares to check the results. This equals 6 x times x is x squared plus 8 times 3 is 24x plus 5 times 2 is 10x plus 5 times 8 is 40. Simplifying, we get 6x squared plus 34x plus 40. Looking at the next question, that equals 5x times 4x is 20x squared. 5x times 9 is plus 45x. Starting with the minus 2 times 4x is minus 8x. And minus 2 times the 9 is minus 18. Simplifying, we get 20x squared plus 45 minus 8 is 37x minus 18. Now what we want to do is take each of these factors and put them on the squares and practice going back the way we did it originally and make sure that we get the same expressions when we're done. So I will need a 2x and an 8 on the top of this square. 2x and then an 8. On this square, we will need a 3x and then a 5. Three x times 2x is 6x squared. Three x times 8 is 24x. Five times 2x is 10x. And 5 times 8 is 40. Looking over at the next problem, we need a 4x and a 9 on top here. And on the side, we need a 5x and a minus 2. Multiplying, we get 5x times 4x is 20x squared. Multiplying, we get 5x times 4x is 20x squared. Five x times 9 is 45x. Minus 2 times 4x is minus 8x. And minus 9 times 2 is minus 18. And then we don't have to go through and simplify. We can compare what we got here to the second step in each of these. And what you can see is that all of our terms are matching. And as we go through this, you can see where the order comes from, because we did these two first and these two second, and so these two end up being in the middle. Same thing here. We have all the same terms as this second step, and it would just be a matter of adding them up. Now, there is something to consider in this analogy. In this situation here, it seems more straightforward. There's something about this side that might cause us to wonder, and it has to do with this square or rectangle and this rectangle right here. And so it says, is there anything unusual about the side lengths? What do you think about this? Well, what we see here is that this side length is minus 2. So this is where the analogy of a square and a rectangle break down, because we usually don't have negative side lengths. But in this situation, the strategy still works. In the second square, the two bottom rectangles have a negative side length. In terms of dimensions, negative lengths don't make sense. And now what you can do is go down and practice converting from factored form to standard form by doing the distributions. And this is actually called mathematically a binomial distribution. Bi means two, like in a bicycle. This bracket here, or this factor, has two terms in it. That's where the bi comes in. So this is a binomial and a binomial. So we call this a binomial expansion. And remember that you will be doing this term times each of those, this term times each of those, and then collecting up the like terms in the middle.